Hello everyone, my name is Siyuan. This is my final project report, an interference reduction in high altitude platform WCDMA systems. First of all, I will do some introduction. It's about abstraction purposes and background. In this paper, I investigate the possibility of multiple HAP coverage of common cell area. In particular, I study the uplink system performance since it is considered as a worst case scenario. In order to obtain further enhancements, I also apply space-time diversity techniques such as single input, multiple output, receive diversity, or multiple inputs, multiple outputs diversity to improve the spectrum reuse in the multiple HAP scenario. I will show the level of improvement using SIMO or MIMO algorithms, the practical limits on the number of HAPs and SIMO-MIMO system dimension in response to traffic demands and the type of service used. We all know the third generation mobile system are gradually being deployed in many developed countries in hotspot areas, but it's not well used. The 3G is not well used in many countries, especially in developing countries. There's one possible cost-effective solution for deployment in these areas is to use high altitude platforms, which is HAPs, to deliver 3G communication service over a wide coverage area. As HAPs are either airship or planes that will operate in the stratosphere, which is 17 to 22 kilometer above the ground. This unique position offers a significant link budget advantage compared with satellites and much wider coverage area than conventional terrestrial cellular systems, such as platforms will have a rapid rollout capability and the ability to serve a large number of users using considerably less communications infrastructure than required by a terrestrial network. In this paper, my purpose is to examine how the unique properties of WCDMA system combined with space diversity techniques can be exploited in multiple HAP uplink architectures to deliver both coverage and capacity enhancement. Okay, for the first thing I do is the multiple HAP WCDMA system setup. In this paper, I use simple geometric positioning of the high altitude platforms to create single environments that are easily be compared and analyzed. In each constellation, the HAPs are located with equal separation along a circular contour as shown in this picture. The separation distance dm along the line from the vertical projection of the HAP on the ground to the cell center is varied from 70 kilometers to 0. all HAPs are assumed to be flying in the stratosphere at an altitude of 20 kilometers. The size of the coverage area assigned to each HAP is governed by the shape of the base station antenna pattern. If we assume that we only have one cell per HAP, then the coverage area is also synonymous with the total cell area of the HAP. And for the user positioning geometry, each user equipment is positioned inside the cell according to an independent uniform random distribution over the cell coverage area with radius r as shown in this picture. The position of each UE inside each cell is defined relative to the HAP base station that it is connected to, and also relative to every other HAP-borne base station. This is necessary in order to evaluate the impact of interference between the different UE HAP transmission paths. And base station antenna pattern. The base station antenna pattern for the simulations were chosen to be simple but detailed enough to show the effects of the main and the side lobes, especially in the non-directions as illustrated in this picture. To get this picture, I write a MATLAB code, which is this, just to keep the. I want to get the gain of. I take the sample of 2 kilometers, 5 kilometers, and 10 kilometers, and to get their gain, and I finally get this plot. Which for okay, and for the user equipment antenna pattern, in this analysis, I assume that each UE employs a directive antenna and communicates with its corresponding HAP base station. Using this assumption, I only need to set the desired maximum gain of the UE antenna we want to use. So this is chosen as 0 dBi for mobile phone and 2 for 12 dBi for data terminal. The antenna pattern of the directive antenna is calculated according to the equation. I show it in the paper, but with a fixed maximum gain instead of fixed main beam width. The beam width is then 5G max. Okay, and for the user equipment HAP radio propagation channel model. In this paper, I used the combined empirical fading model, which is CEFM, together with the free space loss, which is FSO. CEFM combines the results of the empirical roadside shadowing, which is ERS model for low elevation angle, with the high elevation angle results for the L and the S bands. Then for the WCDMA setup, there's a table which WCDMA service parameters employed in the simulations. The different service parameters used in this paper are collected from the 3GPP standard and are summarized in this table in order to account for the relative movement between the UE and base stations. A fading propagation channel model based on equation 6 GMN theta mn equals. Okay, never mind. I used it in the paper is simulated. So after the result, this results in a block error rate requirement of 1% for the 12.2 kbps voice service and block error rate of 10% for 64, 144 and 384 kbps data packet services respectively. Then I do some there's some space-time diversity techniques, and I do some interference analysis. So finally, I got the simulation results. In this simulation, I assume MHAP is uniformly located along a circular boundary with the center of the circular boundary acting as the pointing direction of the HAP space station antennas, which simulate several overlapping cells. See this picture. Here. Yes, see this picture. And the beamwidth of these space station antennas are determined by the radius of the cell coverage area. You can see the first image and the third image. These results are required through running multi-choroid simulations of the multiple HAP system. The aim of the simulation is to assess the effect of adding more HAPs and the impact of using space-time diversity techniques on the system's capacity. The distance dm between the cell center and the vertical projection of the HAP on the Earth's surface is denoted as distance on the ground and is varied from 0 to 70 kilometers with a fixed cell position. The distance to the cell center is also changing the elevation angle θm towards the HAP base station M as seen from the user. The cell radius has been set to 10 kilometers and 13 kilometers, and the HAP altitude is 20 kilometers. Each HAP base station service is 100 users within each corresponding cell. From this picture, it is obvious that using a space-time diversity technique will enhance the interference mitigating capability and improve the overall performance of the multiple HAP system. This interference mitigation technique can also be interpreted as a capacity improvement, which is clearly seen in this picture for a 3 HAP system and in